Hi, and welcome to another video about our HAPTICORE customer test app. This time we'll be taking a closer look at the turning characteristics of your HAPTICORE, as we will talk about our torque and current function. To help you understand how torque and current differ and how you can customize your haptic modes even further with them, we are going to show you everything you need to know. This video is part of a series about our HAPTICORE software solutions, so make sure to leave us a like and subscribe to our channel so you don't miss any announcements and new videos. But for now, let's go. We first need to turn off all other functions, and we start by taking a look at the current function. With the current function, we can set, as the name might already suggest, a fixed current that we apply to the coil of the encoder. This does not necessarily have to be constant, but instead can be increased or decreased linearly within a defined range. With the preset settings activated, for example, we would permanently supply a current of 0.1 amps to the encoder, which would make it slightly increase the resistance during the rotation of the encoder. The current function, however, constantly supplies 0.1 amps to the coil, no matter whether we're rotating fast or slow. You can clearly feel this increased resistance while rotating slowly, but when you start spinning the encoder faster, the current is not adapted to the applied forces, and the perceivable resistance decreases. You can also observe this in the reports. Regardless of how fast we turn, the coil current remains constant at 0.1 amps, which we defined in the current function. The torque function, which we now activate, is working a different way. Here, not a concrete value, but instead a current factor is set. This means that depending on the speed with which the encoder is rotated, the current applied to the coil will be adjusted by the torque factor. This adaptive coil current gives us a more homogeneous haptic feedback with constant resistance as the rotation speed changes. In other words, the current function uses a constant current for a basic low rotation resistance at a lower rotation velocity and decreased friction at a higher speed, while the torque function adjusts the coil current depending on the rotation velocity, using a factor for a more constant haptic feedback. And as with other haptic modes, we also have the option of defining a range for torque and current in which the function should be active, for example from 0 to 180 degrees. As soon as we define a stop angle here, our stop factor is also activated. If we set the same factor here as for the start factor, then the resistance remains the same over the entire corridor. So let's test this right away. After resetting our encoder to the angle of 0 degrees, we instantly get a stronger resistance while we are inside the corridor, which disappears as soon as we get outside of it. However, now we can also make the resistance inside the corridor increase linearly. Therefore, we set the start angle to 0 degrees and the stop angle to 0.001. If you now rotate your encoder and move from 0 degrees up to 180 degrees, you feel an increased resistance, and as soon as you go beyond 180 degrees, the resistance disappears. If you want, you can also combine this with the barrier. We have already set the angles from 0 to 180 degrees in another video about the barrier function, which you can find in the description below. So we activate the barrier function and immediately add the barrier at the beginning and the end of the torque corridor. To prevent errors and to generate clean haptic feedback, you should pay attention to the polarity. We explained this topic in our barrier video as well, so if you haven't watched it yet, you should definitely check it out. In this case, however, we stay in a positive polarity range and therefore set a positive barrier polarity for both the start and stop. And if these customization options are still not enough for you, then you can separate the haptic feedback for the clockwise and counterclockwise directions. For example, we can set a stronger resistance for the clockwise direction and make it half as strong for the counterclockwise direction. Another interesting feature of the torque function is freewheeling. Thereby, our torque function is switched off for a definable time at a certain rotation speed. We'll test this function with a value of 500 degrees per second for the velocity threshold, and as soon as we reach this speed while turning, we want our torque function to be switched off. As we fall below the value, however, the function should automatically activate again after 100 milliseconds. You can experiment with these factors until you find the right combination for your application. In our case, if we now turn the encoder, of course with the barrier function deactivated and with torque function angles deactivated, we feel a resistance when turning slowly, which disappears as soon as we turn the encoder faster and exceed our 500 revolutions per second. If we now turn slower and fall below the value, the timer of 100 milliseconds runs out and we feel the resistance again. To demonstrate this timer more clearly, we set the value significantly higher to 1 second. And if we now activate the freewheeling, we don't feel any resistance for another 1 second, even though the speed has fallen below the limit. If we now wait for a second, our torque factor is added again and we feel the resistance. If you switch to the current function and you compare both of them side by side, you will notice that the available fields do not change at all. However, as explained at the beginning of the video, you should keep in mind that with the current function, we apply a fixed value to the coil, meaning no adaptive resistance at changed rotation speed, whereas with torque function, we apply a factor to increase the current according to the speed for a more homogeneous haptic feedback. And at this point, another short note about the different settings. The different fields are linked and oriented to the highest value as long as 0 is entered. If, for example, we do not enter a value for both start and stop angle, there is no corridor in which a rising or falling resistance can be built up. In this case, only our start value is used for any movement of the encoder. However, as soon as we add a stop angle and thus open a corridor, the corresponding stop current value is activated, and in this case, we would create a decreasing resistance while turning the encoder clockwise. The same applies to the counterclockwise values. As long as no separate value is set here, the clockwise values will also be applied to the counterclockwise fields. Finally, we can also deactivate the current and torque function for certain directions of rotation by activating the function only for clockwise or counterclockwise instead of both. Now you know the difference between the torque and the current function. Did you miss a few things? No problem. Just rewind the video or take a look at our documentation for the customer test app, which you can find in the download folder. And as usual, if you have any questions about our software solutions, our HAPTICORE products and Eval Kits, do not hesitate to get in touch with us. Our customer support team will be happy to assist you. Otherwise, leave us a like and subscribe to our channel to make sure you don't miss any announcements and new videos. Have fun trying out our HAPTICORE technology and see you in the next video.